Okay, so today we're going to talk about spur gears. And when we talk about spur gears, there's some relevant features that we have to define. First, this is my attempt at drawing gears, as rough as it is. When we measure the diameter of a gear, there are actually several diameters on a gear that are relevant to us, but only a few that really, or only one really that gets used a lot. And there is an inner diameter. It's like that. The inner diameter is from the inside of the teeth to the inside of the teeth. Then, of course, there's an outer diameter that goes to the outside of the tooth. Unfortunately, when we go to describe gears, we don't use either of those diameters. So what we have to define is something called a pitch circle. A pitch circle is kind of like the gear's space that it really occupies. Because the teeth of these gears mesh together, a single gear when it's working doesn't occupy the whole space all the way out to the outside of its teeth. So the pitch circle is a circle that looks something like this, that is somewhere between the inner diameter and the outer diameter of the gear. And when two gears are meshing together like this, their pitch circles are tangent. They just touch each other. The outer doors are locked today? So that pitch circle is what we use to describe the gears. So the pitch diameter is the diameter of that pitch circle. And when we're looking at spur gears, when you see the letter D, that's the diameter that it is specifying, unless it has a little notation beside it. Now, as you can see, these teeth mesh together, and they don't go all the way into the bottom. The distance between the end of the tooth and the bottom of the inner diameter, basically, of the next gear is what we call the clearance. Obviously, the less that clearance is, the stronger the connection is between the gears, less likely it is to snap off a tooth and so on. The depth that the gear goes into the tooth goes into the next gear. You know, for example, these teeth come in, so it's the outer diameter of this circle here. From the outside of this tooth into that spot, the depth that that tooth penetrates is what's called the working depth. The distance from the outside of the tooth all the way in, that's called the hole depth. Hole is incomplete, not hole is in a drilled hole. So those are the basics of the gears meshing together. Next, we have to look at something called the Addendum and the Addendum. From this pitch circle, you can see there's a piece of the tooth that sticks out outside of the pitch circle. I didn't draw my teeth very well here. I just did the ones where they mesh, and the rest of them I drew them pretty sloppy. That is called the Addendum. It is outside of the pitch circle to the outside of the tooth. The inside of the pitch circle to the inside of the tooth, or to the inner diameter, that is called the Addendum. Now, if we want to figure out what the pitch diameter is for two gears, Pretend those look like circles. Now I'm just going to draw my teeth blocky here. Like this. Pretend those teeth look like they'll mesh and not break off. So anyway, let's say we have the outer diameter of one gear is 6 inches. And the outer diameter of the other gear is 8 inches. If I give you then that the center to center distance between the gears is, oh, what's that going to be? 3, 4, 6.48 inches. We can use that information to calculate a working depth. The working depth is the difference between if the two gears were just touching the ends of their teeth and what the center to center distance is when the gears are meshed together. If the gears were just touching at the outside of their teeth, the distance between centers, you would have the radius of this gear and the radius of that gear, right? So what's the radius of this gear? Well, the radius here is 3 inches. Radius of this one is 4 inches. So that would make that center to center distance, the sum of the two radii is 7 inches. But the actual center to center distance is 6.48. So we subtract those two and we get 0.52 inches is the working depth. Does that make sense? So that is how far these teeth overlap here. It's 0.52 inches. Any questions on that? Does that make sense? Yeah. So that knowing that working depth allows us to find the pitch diameter. If I take that working depth, if I were to divide it, the pitch circle for each of these gears is going to fall in the middle of that working depth. It's going to cut right through the center of that. Like that. So half of that working depth is going to get subtracted off of each radius. Does that make sense? But now that's the radius. How much are we going to lose off the diameter? Well, we're going to lose the same on the other side as well. So the pitch diameter for a circle, for one of these gears, is equal to the outer diameter minus the working depth. So the pitch diameter for this gear here, it's 6 inches minus the 0.52. That's going to be a 5.48 inch pitch diameter. Here, 8 inches minus the 0.52. That's going to be a 7.48 inch pitch diameter. Why am I spending so much time talking about pitch diameter? Well, because something called the, what's that? Pitch is used on threads. It's also used on gears. The pitch of a thread is, you have to have two threads have to have the same pitch to mesh together. Two gears have to have the same pitch to mesh together too. In a gear, what the pitch describes is how far the teeth are apart and how the teeth are spaced and how wide they are. Two gears must have the same pitch or they won't mesh together. I mean, you take two gears and they may seem to mesh together, but if their pitches are slightly off, when they get up to high speeds, they're going to either lock up or chip out, bust teeth out. So in that packet I gave you yesterday, we were talking about cutting speeds. Starting on page 247 of that packet, there's a table that goes through all of these quantities of a spur gear and how they all fit together. So for example, the pitch of a spur gear, which is going to be abbreviated with a P. Pitch is the number of teeth divided by the diameter, the pitch diameter of the circle. So N is number of teeth. D is the pitch diameter. Now, P here, the pitch, is sometimes referred to as the diametric pitch, but that is just the pitch. That's what its common name is anyway. There is something called the circular pitch. The circular pitch describes the distance. See, I have my teeth here. What circular pitch is describing is the distance from the center of one tooth to the center of the other at the surface of that pitch circle, of that pitch diameter. So it's not at the outer. Notice I didn't draw that in at the very outer edge. It's not the inner edge. It's at that pitch circle. And that can be found by taking pi times that diameter, that pitch diameter, divided by N. So P with the little c by it is circular pitch. So pi times your diameter is the circumference of that circle, the pitch circle, divided by your number of teeth. That would be the distance, dividing it up per tooth, the distance between teeth. Or, you know that N over D is the pitch. So 1 over the pitch is D over N. So I replace D over N with 1 over P. So that's just pi over the pitch. Now in your packet they use 3.1416. We all know that that's just pi. So let's say we have 2 gears. Gear A has a pitch diameter of 4 inches and has a number of teeth of 28 teeth. Gear B has a pitch diameter of 7 inches. How many teeth would gear B have to have for these 2 gears to mesh? Well, let's find the pitch of gear A. Remember, D is pitch diameter. The pitch is N over D, so number of teeth over that pitch diameter. This is 28 teeth over a 4-inch pitch diameter, which would give us a pitch of 7 teeth per inch. So it's a 7-pitch gear, which means that this gear must have a pitch of 7 as well. So to figure out what that number of teeth has to be, pitch has to equal the number of teeth over the diameter. Our pitch has got to be 7. We're looking for N, and D is a 7-inch diameter. So how do I find N here? Well, N has been divided by 7, so to get rid of the 7, we multiply by 7. 7 by 7 is 49. So that gear has to have 49 teeth if those 2 gears are going to mesh properly, to have the same pitch. Okay. Now there are other formulas. The packet, like I said, starting on page 247 there and continuing for a couple pages, has several formulas. Most of them are just rearranging, like the pitch diameter. Which is just D. Well, that can be found since the pitch is found by the number of teeth divided by the diameter. If you just rearrange that formula, D is equal to the number of teeth divided by the pitch. Or you could rearrange that circular pitch formula. Remember, given PC is equal to pi D over N. We could solve that for D. D is equal to N PC over pi. But those are all things you guys can do. We had algebra last semester. You guys can rearrange those formulas on your own. I want to take a look at some of the other formulas that may not be quite as obvious from the others. Outside diameter. This is going to be D with the O on it. Remember, D by itself is the pitch diameter. D with the O is the outside diameter. We tend to not really use the inner diameter for any of these calculations. But the outside diameter for most gears is going to be N plus 2 divided by the pitch. The clearance on a gear tends to be a function of its diameter and number of teeth. Its pitch diameter and number of teeth. So the pitch diameter is the number of teeth divided by the pitch. The outside diameter would be basically what you would need for 2 extra teeth. So let's say that we have a gear that has a pitch of 6.25 and let's say it has a pitch diameter of 4 inches. To find what the outside diameter would be off of that gear, we're going to start with this formula here. We're going to put 4 in for the pitch diameter. N is what we're looking for, the number of teeth. P, the pitch, is 6.25. Solving for N there, multiply by 6.25. Got 25 equals N. So that gear has to have 25 teeth. Now that we know that, we can find the outside diameter by putting 25 up here, 25 plus 2, over the pitch of 6.25. So 25 plus 2 is going to give us 27, divided by 6.25. That outer diameter should be 4.32 inches. What that means, again, is that the teeth are sticking out how far? What would be the whole depth? So let's think about this. We've got a pitch diameter of 4 inches, and we've got an outside diameter of 4.32 inches. The whole depth, remember, I really do need to improve my artwork at some point in my life. Not going to be today. The whole depth is from the outside of the tooth to that inside diameter. That's our whole depth. Now the outside diameter goes all the way out. That's the 4.32. The pitch diameter, the 4, goes from here to here. Do we have enough information there to find the hole depth yet? No. We can, however, find the working depth. The working depth is always going to be the difference between the outside diameter and the pitch diameter. So the working depth here is going to be 0.32 inches. If I knew the clearance, I could then find the hole depth. So I would have to know the inner diameter to have a perfect clearance. If I give you that the hole depth is 0.38 inches, the clearance has to be the hole depth minus the working depth. So 0.38 minus 0.32 gives us 60 thousandths, or 0.06 inches of clearance. What do you guys think? The hole depth, I had to give you that. That had to be given information. Now there are some, if you look on page 248 in your packet, there are some of the items in that table that have an asterisk by them. Generally, it's starting with the addendum and working mostly all the way down to the clearance. You know, this formula for the clearance is always true. They're not using that one in the book because it's not very often you have both the hole depth and the working depth. Usually you have the pitch or the pitch diameter. They're also using the circular pitch. Those that have that asterisk by them there, like I said, from the addendum down to the clearance, those formulas only work for certain types of gears. The note on bottom, it says for a 14.5 degree involute and full depth gear. This is 248. All that is saying a 14.5 degree, that is the spacing between teeth. You know, 360 degrees is a full circle. That's 14.5 degree spacing from tooth to tooth, which is another way of describing the pitch. So just know that those with the asterisks by them, we're going to use those formulas for everything we do. But in practice, those do only apply to certain classifications, certain types of gears that meet certain classifications. Okay, so you start at like the addendum there. If you look over on the far right side of that table, so addendum is like the third or fourth one from the top. On the left column, it says addendum. It says outside diameter, root diameter, then addendum. Follow that over to the right side of the table. There's an asterisk by those, by the formulas. All those formulas have asterisks by them. And you go down the table, the next like 5 or so have those asterisks by them. Those only apply to a 14.5 degree involute gear. Most gears fit that qualification, so it's not a big deal. But just put that in there to make sure that you know that's not an absolute formula. The other ones are always absolute. The ones with no asterisks, those apply to any spur gear. But those only apply to certain special classifications of gears. Okay, what I want you guys to work on, I've been cutting you guys pretty short of work time lately. So in this packet, page 251 through 252. I want you guys to work on 1 to 53 the odd. This is mostly just a practice of picking the information out. I mean, the first several is just a table, so it's fairly easy. But the next section, the next couple sections, is a practice basically of picking out the information that you have, finding a formula that contains that information, and then applying that formula. And it's a skill. It's not as easy as it would look. The first set's fairly easy because it's straightforward. What it's asking you for, you can go look at that table. Remember, that table is on page 247 and 248. You can look at that table, and it should have a formula right in that table that gives you that. Some of the others, you'll have to find a formula in that table that uses that as one of the inputs, and you have to solve the equation. So you have to work some of them backwards to get to those amounts. So I'll let you guys have the last 20 minutes to get started on those.